Perfect. Thank you very much. As Keith was just saying, I'm currently a postdoc, and I'm presenting some of the work which I did when I was a PhD student at Imperial, on how we can use some probabilistic machine learning tools in order to kind of put some physical interpretability into spectroscopy methods, and how we can use some of the more advanced machine learning techniques in order to come up with methods which are better for incorporating physical knowledge, but still maintain kind of very good levels of accuracy. So jumping right in, I'm hoping that a lot of people in the audience are familiar with the basics of spectroscopy. It's a non-contact measurement technique, with the basic idea being that you shine some light on a sample. You look at what light is either transmitted through the sample or comes back as a reflection from the sample. And there's a ton of different types of spectroscopy, but one kind of unifying thing for a lot of the different forms of spectroscopy is this linear relationship, where essentially what you say is that we say each chemical species is going to interact with light in kind of specific way, in some specific shape. It's going to absorb more at some wavelengths than at other wavelengths. And whatever sample we see is going to be some approximately linear combination of the underlying signals. So if we have a signal with a lot of some chemical species A, we would expect that the thing that we observe should have peaks and troughs in similar locations than to the chemical species A. And just to kind of give a more pictorial example, if we have a spectroscopy setup where we have two chemical species, species 1 and species 2, and species 1 has a pure component signal which looks like this on the left, with a peak at around kind of this fake -5 wavelength, and chemical species 2 has a peak further at a higher wavelength. But there's 20% of chemical species A and 80% of chemical species B. What we would expect to see is some combination of the two, where there's peaks in both of the locations, but the peak associated with the second signal is significantly higher, which is just reflecting that there's a lot more of chemical species 2 in the sample. And of course, because we live in a real physical world, there's always going to be some amount of measurement noise in our observation. So this is kind of like a very nice just so story for how spectroscopy works. But in reality, kind of the world's a bit more complicated than that. And specifically, something which we know is that depending on what the conditions are when you make your measurement, we actually expect these pure component signals to vary. So it's not that you have like this one single pure component signal. So as soon as whenever you have a particular chemical species, it's always going to kind of interact with light in the same way. Actually, it's going to interact with light depending on things like what the temperature is, what the crystal structure of that particular of this chemical is when you're making the measurement. Even changing from one spectrometer to another spectrometer is going to have kind of an implicit effect on what the pure component spectra is, because each measurement device is slightly different. So the change to the kind of very classic model of spectroscopy, which we were working on in my PhD, was, okay, how can we incorporate this slightly more complicated model of the world, where the pure component signal can vary from sample to sample and still make kind of good predictions? So the difference from the completely standard spectroscopy in this equation is this new thing which we've introduced, XI. XI is representing these kind of changing conditions, and we make a couple of assumptions about them. Number one is that we assume they're kind of not things that we know when we're making the measurement. You know, you don't necessarily have a temperature probe in your sample when you take your measurement. And they're therefore things that we need to kind of be able to make some estimation of. So what the actual setup would look like for us is something like this. Very simple toy example is we have a data set, and the data set consists of two sets of spectra, one training set where we see the spectra, and we also know what was in the chemical, the particular substance which produced that spectra. So that's why we've kind of colored the spectra on the left. That's just saying that when we're going through and kind of fitting our model, we know what was in those samples, and we can use that information in order to try and work out what the pure component spectra is and what the underlying conditions were when we were taking that measurement. So what we see is that there's kind of this peak shifting from right to left, and we also have a change in the intensity of the peaks depending on how much of substance A or substance B is. And then we also have a set of test measurements where we don't necessarily know what was the, well, we don't know what the chemical makeup was. And the ultimate goal of spectroscopy typically is we want to work out what was in this set of test spectra where we don't have prior knowledge of what precisely was in there. So this kind of slightly more complicated setup, this actually presents a bit of a challenge, and specifically presents a challenge for this thing called identifiability. This is a non-identifiable system. So technically, identifiability is defined as being for each set of parameters of your model, there is just one unique maximizer of the likelihood. Or there is one set of parameters which maximizes the likelihood. And that obviously isn't true in our case. So for any particular choice of F and R for everything up to kind of the last component, I can always pick the last component such that it will exactly match whatever observation we have. So what we're looking for is kind of some solution which is going to let us take these infinite number of solutions and kind of narrow down to solutions which make sense. And kind of just returning to this very toy kind of pictorial example to kind of get a better sense of it. This is the example which I presented kind of right at the start. We have what the true pure component spectra are, and then what our observation is. And, you know, it, I think, makes a lot of sense to most people when they see it. They see, you know, there's a peak here, there's a peak here. And then what we observe is a combination of the two, and you see the two peaks. But unfortunately, these two signals add up to be exactly the same as these two signals. So what I've done here is I've kind of added an additional sinusoidal signal to both, and the peaks of one cancel out with the troughs of the other. And when you add them together, you end up with an identical fit to the true pure component spectra. And what we're looking for is how can we come up with methods which are going to still give us this flexibility of allowing the pure component signals to vary from one sample to another, but that rule out these kind of slightly ridiculous looking solutions to it and only leave us with kind of physically plausible ones which we can use to make good estimates. So kind of our key conceptual idea here, the thing that I think was our main contribution, was saying, oh, there's actually kind of a nice way we can do this in a Bayesian way, where we can use type 2 maximum likelihood estimate via a Gaussian process latent variable model as a regularizer in order to get the correct solution. And I appreciate I've just said several words which maybe people aren't so familiar with, and I'll kind of introduce these in the next couple of slides. So type 2 maximum likelihood estimation is kind of in very simple terms, it's a Bayesian approach to model selection. So it's often motivated as saying this is a mathematical encoding of Occam's razor. Occam's razor is this kind of philosophical principle that if you have two solutions which both kind of explain the world equally well, you should pick the simpler one. And kind of mathematically, the way that we kind of translate that is we say, okay, we're going to be Bayesian, we're going to say we have priors about what the world could look like. And given kind of two sets of priors, if both of the priors fit the data equally well, you want to choose the prior which could fit a smaller number of data sets. And I think perhaps the way that most people kind of interact with this the most, if they're in a machine learning community, is via Gaussian processes. So Gaussian processes, which I have kind of a couple of figures of here, they have this nice behavior where they kind of automatically pick how smooth they should be. And it makes them kind of a really nice technique to work with when you have kind of fewer data points and you have relatively low dimensions often. What they're doing is they're optimizing this log marginal likelihood, which is another name for the type 2 marginal likelihood or log marginal likelihood. And it's going to pick the solution which is kind of the smoothest solution, which does fit all of the data very well. So on the left, we have a Gaussian process, which is kind of not fitted yet. And we can see it actually fits the data incredibly well. It goes through kind of each data point almost exactly. But the problem is that kind of no matter what data set I had picked, I could have picked a very weird set of points and observations here. And still with this kind of very, very sharp prior where there's no smoothness at all almost, I could have fit the data almost if I'd picked white noise here. Whereas the one on the right, there's actually a much smaller number of functions which are this level of smoothness and still are capable of fitting this data very, very well. And you get this kind of very nice automatic trade-off between kind of the complexity of the model and the fit of the model if you kind of take this approach. And what we wanted was to take this same idea of pick the simplest model that you can, which still describes the data very well, and then use it to fit a model. We're in a slightly complicated setting compared to the regular Gaussian process, and that's just because we have a unobserved input. So we have a latent variable, and this puts us in a Gaussian process latent variable model, which was kind of introduced in the early kind of around 2010, and people have kind of worked out the nice maths. Sadly, there isn't quite enough time to go into it. But the key idea for that was that, we're just going to say that we have a high dimensional observation y, and we have a low dimensional latent vector. And what we're going to do is we treat kind of each output of the observation as being independent, and we place a Gaussian process prior over it. And by doing this, we can kind of get a nice Bayesian posterior for the latent space. If people are familiar with it, they can kind of think of this as a non-linear generalization of principal component analysis. So our Bayesian model is not identical to this. So what we do is we assume that each of our pure component signals is this kind of nice smooth variation over both the observed wavelength, but also this unobserved latent variable. And what we're going to do is we're going to try and find the latent variables and also the pure component signals, which preserve this nice kind of smooth mapping, but also fit the data very, very well. So this is our prior for the functions, but we also need to put priors on both what a latent variable is because that's unobserved, and this is just very standard normal spherical normal distribution, and then also for some unobserved weights. So for our test data, because our weights are unobserved, we need to put a prior on them. And this prior is actually pretty flexible. The things that you need to have is that there's kind of this well-defined KL divergence term, and also that it has a well-defined second moment. But you guys will need to read the paper, I'm afraid, to get the mathematical details because there's not quite enough time for me to present it here. And then given these priors, what we would really like to do is to find kind of the exact posterior, which is just calculated using standard Bayes rule. Sadly, this isn't going to turn out to be possible, and that is, as always, because of this denominator of the fraction, which is in fact a high dimensional integral. So instead, we're going to do a variational inference approach. I'm afraid I'm going to have to give kind of a very short overview of variational inference, but the basic idea is that we have this complicated posterior, which we would really like to get at. And what we're going to do is we're going to approximate that using some simpler distribution. Specifically, we're going to pick a parametric family, and then we're going to kind of fit the parameters of the parametric family such that they match the posterior as closely as possible in some sense. The kind of key things for this, though, is that this changes a kind of high dimensional inference problem into being an optimization problem, makes it much more tractable. So what we're going to do is we take this elbow and we optimize it with respect to parameters of the distribution of the latent variables and also the weights. And if people have questions, then read the paper or ask for further details afterwards. The one final thing to note is that this is a non-convex optimization, so you do often need to do things like random restarts, and there's some other tricks which we present in the paper for how to get this optimization to actually work nicely. So returning to the example which I kind of introduced at the start, we have this toy problem. We have two distinct peaks. So they're kind of shifting backwards and forwards, and also the amount of each chemical is moving around. And what are we able to learn by using our approach? So as we would kind of hope, we're able to recover a good estimate for what the fractions of component 1 and component 2 were in the test set. So this is the thing that kind of you most normally care about in a spectroscopy. We also get a good estimate for what the conditions were. So the conditions are kind of, there's no reason for them to exactly line up, but we do kind of keep the same ordering up to kind of a factor of -1. We also get a good estimate for what each of the underlying pure components was and how they vary according to this set of conditions. And it's kind of a nice proof of concept. And then we also applied this to some real data, and we were able to, once again, take a real set of data with some mixture of training stuff where you know what's in it and test stuff where you don't. And we're able to kind of spit out these three physically understandable pure components. Likewise, we have we're able to get good estimates for what the pure component weights were. So this is the this is a 3-component mixture. So everything, because it all sums up to 1, is going to lie on this simplex, which is what we've kind of projected stuff down to here. The true points are shown as blue dots, and our mean estimates, as you can see, are kind of very, very close to what the values you would hope them to be were. Also, if we're doing an approximate Bayesian method, we kind of do get these nice uncertainty estimates. Finally, we are able to actually extract what the underlying cause of this variation was. In this case, we happen to know the cause was temperature, and the temperature was known. And if you plot the latent variables as against colored by temperature, you can see there's this very nice structure that emerges where the first latent variable, kind of the most significant latent variable that we find, is able to recapture like what the temperature of the measurement was actually at. And it gives this very nice physical interpretability and some kind of confidence that the model is actually learning something meaningful. Just to kind of finish up, because I think that my time is almost over. This work was published in AI Stats. I don't know if the full proceedings of the machine learning research for that are out yet, but I put up the archive link if anyone wants to read some more, kind of get into the actual detail of the maths that I wasn't able to get into in this particular talk. And also we have a follow-up work, which we're currently kind of preparing for publication with several improvements. So the method that is currently published is quite difficult to optimize, and we have to include several tricks in order for it to work. And also it requires that you have all of the pure components known on your training set, and you need to know exactly the number of pure components. So if any of those things are things that kind of would interest you for your data, if you kind of hold on for a couple more months, there'll be a technique which is significantly easier to use. And finally, just to thank my amazing co-authors, without whom there is no chance I would have been able to do it. And thanks to the various funding bodies which allowed us to do this research.